Welcome to part 4 of the tutorial. We'll continue discussion of fault tolerant optimization from the last lecture. We saw in the last lecture that if the cost functions of the different agents are independent of each other, meaning that they have no redundancy, then this problem that we have stated at the top of the slide is not solvable as stated. The goal of that problem is to compute an output that minimizes an argument that minimizes the aggregate cost over all the good agents. And we argued that if the functions are independent, then that's not possible. And then we discussed a way of weakening the requirement by using this weight distribution that is different from non-uniform over the good cost functions. And then we discussed the cost functions that have redundancy. In particular, we discussed the notion of exact resilience, where we argued that this T resilience is achievable if and only if 2T redundancy is available, where T resilience meant that we want to compute that argument precisely, meaning we do want to compute an argument that minimizes the aggregate cost over all the good agents, even if some of the agents are faulty, in particular up to T agents are faulty, and without actually knowing which T agents are faulty. And that resilience can be achieved if and only if we have this so-called 2T redundancy property. And this property that is stated on the slide, we discussed it last time as well. So I won't repeat it. I won't discuss it again today. But the goal today is to consider a weakening of this exact resilience and consider approximate resilience, which gives up a little bit in terms of the resilience required. And therefore, the hope is that we can weaken the requirements on the cost functions as well. So the approximate resilience, intuitively, the goal is not to find any more a value that is strictly inside this set, which is the argument, the set of arguments that minimizes the cost, the aggregate cost over all the good agents. In some cases, that argument may be a single point. In general, it might be a set. But the intuition is behind approximate resilience is that we won't insist on finding a point in this set, but we are willing to accept a point such as this one, which is within some distance, parameterized here by epsilon, of that set in yellow, which is the argument of sigma fi of x, where I belongs to set G of all the good agents. So that's what we really want to achieve, but we will define the requirements slightly differently. And the intuition is that in a system where at most T agents are faulty, at least n minus T agents are fault-free. And in the situation where more than n minus T agents may actually be fault-free, we cannot really distinguish that from a system in which a subset of the n minus T agents actually fault-free and the remaining agents are faulty. To put it differently, even if more than n minus T agents are fault-free, the fault-free agents actually don't know that, and they have to allow for the possibility that exactly n minus T of those agents are in fact fault-free, or any n minus T agents of those n minus T agents from the set G are actually fault-free. So keeping that in mind, we define T epsilon resilience, which is a relaxed version of T resilience, as follows. The goal of T epsilon resilience now is to find an output, such as that, which is within distance epsilon of this argument, where I replace the set G on the previous slide with this set S. The set S is any subset of size n minus T of set G, meaning set S contains any n minus T good agents. And I want this point to be within distance epsilon of every such set. That's my goal. That's my weakened version of resilience requirement that we call T epsilon resilience here. But again, intuition is that we are within distance epsilon of the true output of the problem that we set out to solve. At least that's the intuitive goal, but it's stated this way. These kinds of resilience requirements have been considered in other settings as well, in the context of robust statistics, particularly robust mean estimation, and in other contexts such as fault tolerant state estimation. Here we are considering the resilience in the context of distributed optimization, where the cost function has the global cost function is summation over the cost function of the individual agents. So to achieve that sort of resilience, this weakened approximate resilience property, we're going to introduce a different notion of redundancy, which is relaxed notion compared to the 2T redundancy we saw earlier. So let's consider, as before, there are n agents up to t might be faulty. Let's take any set S that contains any n minus t good agents, and any set S hat that is a subset of S of size n minus 2t or more. And we will require that the argument over set S and argument over set S hat, they should be close to each other as well. So this parameter is the parameter here. So what it is essentially saying is that the arguments that minimize the global cost over all the agents in set S are not very far from the arguments that minimize the cost, the aggregate cost over a subset of S of size n minus 2t or more. So that's, in some sense, n minus 2t agents suffice to estimate approximately the argument for the entire set S, or the aggregate cost over the entire set S. For the exact case, the 2T redundancy required that this epsilon was effectively 0. I won't do a numerical example, but this is a setting where this so-called approximate redundancy may be available. So we saw the linear regression problem previously, where we did not actually consider noise, at least in the example that we discussed. But in general, the data may be noisy. So Y may be linearly related to X through this vector AI. However, there may also be some noise in that relationship. Ideally, noise would be 0, but in reality, it may not be. And we want, given Y and A, so agent I knows YI and AI, but the agents collectively know Y and A entirely. Some of the agents will be faulty. Noise is unknown, but given Y and A, we want to compute X star. Because the data is noisy, maybe we cannot compute X star exactly, but we want to estimate X star approximately. And here's a numerical example that I won't dwell on, but this is some random data we generated for X star equal to 1, 1, using this value of A. This is actually what we call Y, in fact, so I should have called it Y on this slide as well. But if you estimate epsilon for this data, for this particular cost function, Fix equal to, if you want to again call this thing Y, to be consistent with the previous slide, then the epsilon ends up being 0.089 if our calculations are correct. And so to put it differently, these cost functions that result from this assumption, these assumptions satisfy, these cost functions satisfy to this particular redundancy property with t equal to 1 and epsilon equal to 0.089. Okay, this is just a numbers with the epsilon we computed numerically. The exact numbers are not that interesting, but just wanted to point out that this notion of redundancy can occur in practice. And in fact, the epsilon parameter can be quite small if your noise in this particular example is not very large. So this is what we are able to show, that 2T epsilon redundancy is necessary for T epsilon resilience, and 2T epsilon redundancy is sufficient for T, 2 epsilon resilience. So there's a gap here between the necessary and sufficient conditions at this point. So I won't do the necessity proof here or the sufficiency proof for that matter, but just wanted to be aware that results of this sort exist, and there are algorithms that can achieve this property given this redundancy condition with some additional assumptions. I'll come to those algorithms later. Rather, I'll talk about the distributed algorithm later. Here's a centralized algorithm. And if you recall, we also discussed the centralized algorithm for the setting where we have 2T redundancy and we achieve T resilience. We did not discuss the distributed algorithm yet. And this algorithm that I'm presenting next is a generalization of the algorithm that we discussed previously in the last lecture. So the algorithm is centralized now, which is to say the server has all the information it needs to solve the problem. And in effect, the agents provide their entire cost function to the server, and a server can utilize that information to produce an output. The faulty agents can provide the wrong cost function. So this is what the server does. So server picks, there are n agents that provided n cost functions. Server picks any subset, let's call it T, uppercase T of size n minus T agents, any one subset like that. And then for each subset T hat of T of this size, we compute this quantity. So what is this quantity? First step, remember we chose T hat. We pick any one argument xt from this set, which is the set of arguments that minimizes aggregate cost over uppercase T. Then you compute the distance of that point that we chose up here from this, which is the arguments that minimize the aggregate cost over just T hat. And let's call that distance RT T hat. So again, what is X? What is this thing? This is an argument that minimizes the aggregate cost over set T. This quantity is the distance of that point from the arguments that minimize the aggregate cost over just T hat, which is a subset of T. And so that's RT T hat. And now we're going to define RT, which is the function of just T, right? We have picked T and T hat, which is T hat is a subset of T. Now we're going to find the largest such value over all. So this maxes over all sets T hat. So we computed RT T hat for a given T and T hat. For a given T, we'll look at all possible T hat and then take the maximum R, and that's what we're calling RT. And the way to think about RT would be to say that, what we're really trying to find is the argmin over set T, but how well do the subsets of size, smaller than the subsets of T, that the argmin of the subsets of T, how well does that approximate argmin over set T itself? And so this is RT pictorially. And then we are going to choose so remember we did this for one set T of size n minus T. So we picked T size n minus T. We're going to do this for every such set T of size n minus T. And then having done that, this is a very exhaustive search. It's expensive, but we're just trying to give an existence proof here of an algorithm. And then we'll pick a set S for which this RT is the minimum over all such sets of size n minus T. And then the output is the argmin for that set. If you did not follow the details of this, not terribly important, but the point is that there exists a procedure that if you use this algorithm, then you can achieve T to epsilon resilience, provided that the data has, or the cost functions have 2T epsilon satisfied 2T epsilon redundancy. But this is a centralized algorithm. What we really care about in our context are distributed algorithms. And so I'll give you an example of a distributed algorithm later on. In fact, I did not give you a distributed algorithm for exact resilience either. And the algorithm for both of them is the same. And we'll come to that later today. So the notions of fault tolerance that we just discussed is a so-called approximate resilience. Before that, we talked about exact resilience. And there are other versions as well. So in fact, the first notion of approximate resilience that we discussed was this notion of non-uniform weights in the context of independent functions. What we observed is that the goal of finding argmin over aggregate of all good cost functions is really identical to computing the argmin of a uniformly weighted average of the cost functions of the good agents. Then we said that if the functions are independent, you can't really do that, but I can approximate the uniform weight vector by a non-uniform weight vector, and we can give you some properties on the non-uniform weight vector itself. So, but that's one way to relax the resilience requirement by allowing for non-uniform weights. That's one way to pose the relaxation. The other second method is what we just discussed, the 2T epsilon resilience, where we are bounding the distance between the argument that we are actually wanting to find versus the output of the algorithm that we produce, the distance between those two. So the distance here is between the arguments of the argument we wanted to find and the argument that we are actually able to output. A third way to relax is to say that, look, what we're really trying to find is the true optimum, and the the cost of all the good agents, or aggregated over all the good agents, at that true minimum is, suppose the true minimum is x star, is the sigma fi of x star I belongs to G. That's the cost. Now, maybe I cannot actually produce an argument x star, but I can produce an argument x hat. Then what I want to do is I want to bound the difference between this value and so let's just call the aggregate cost to be f. F is a summation fi over I belonging to G. So what I may be trying to bound is this instead, right? This value. So I'm not giving a bound for x star minus x hat, that distance, but I'm giving you a bound between the cost values at x star and x hat. So this is slightly different from, so this is distance in the arguments. This is the distance, or difference between the values of the cost function at the output versus the true minimum cost. And there is some work using this particular metric as well. We won't discuss that today in any detail. So next, what we're going to talk about are some algorithm. In fact, really only one algorithm, but that algorithm has a step where the server in the centralized setting, in the server-based distributed optimization setting, the server is going to perform filtering on the gradients, and the different algorithms we'll discuss really only differ in the filter they're using. So just one algorithm, but different filters. So like I said earlier, maybe a couple of lectures earlier, there are two different architectures that we have discussed for distributed optimization. For the fault tolerance part, we are going to focus mostly on the server-based architecture. But before I get to that, let's talk about the peer-to-peer case. We'll come back to the server again. So in the peer-to-peer case, there is no trusted server. The peers have to collaborate with each other directly without the help of a trusted server. So here's an example of a peer-to-peer network, which is a complete graph. It's complete in the sense that every agent can talk to any other agent directly. Right? The agent 1 can talk to 2, 3, and 4. If the network looked like that, this would be incomplete because there is no direct edge from 1 to 5. If 1 wants to send some message to 5, it has to go through agent 2. But in this simple example, the network is complete. But there are no trusted nodes. Anybody can be faulty. Suppose t equal to 1, then one of the agents can be faulty. Now, if the agent is faulty, if you want to implement an algorithm, an iterative algorithm such as the one we discussed a while ago now, if you recall, what the agents have to do in each iteration is to send to the other agents their current estimate, which we call, in this case, x4, the estimate of agent 4 at the current time, and the estimate has to be sent to all the other agents. If agent 4 was a well-behaved or a good agent, it would send the value of x4 correctly to everyone. However, in this case, agent 4 is faulty, so it actually sends potentially wrong values, but more importantly, it can actually send different values to different agents, because agent 4 can talk to agents 1, 2, and 3 over their own dedicated links. Agent 4 can lie basically about his state, but also lie differently to different agents. And this ability to equivocate in the sense of telling different people different things, not just wrong, but wrong in different ways, causes additional headaches to these kinds of algorithms. This would be different from a fault agent lying identically to everybody, meaning I may send you a wrong value, but I send the same wrong value to everyone. That's a little bit nicer behavior. It's not nice in the sense that I'm still lying, but at least I'm lying consistently. That makes life a little bit easier than lying inconsistently or equivocating. So there are a couple of ways of dealing with this kind of behavior in a peer-to-peer setting. One way to deal with it is to actually essentially prevent equivocation, which is to say, we somehow force the faulty agent to either send the correct value or if it is going to send the wrong value, we force it to send the same wrong value to everybody. Of course, the other agents actually don't know necessarily whether they're getting the right value or the wrong value, but they are at least assured that everybody's getting the same value, whether right or wrong. And I won't discuss the details, but there exists something called the Byzantine Broadcast algorithm that was proposed more than 30 years ago now, which essentially defeats equivocation. So there is a way, the algorithm takes many messages, many rounds of messages. However, at the end of it, we can be sure that every agent, in this case, agents 1, 2, and 3, will accept the same or identical value from agent 4. So even though agent 4 may be trying to send different things to different agents, because now the communication happens through this so-called Byzantine broadcast primitive, at the end of that primitive, they will all have the same value. So in this example, for example, they all get 0. Even if 0 is wrong, at least it's identically wrong. And that helps life a little bit. In particular, we can actually simulate any server-based algorithm if we can implement Byzantine broadcast, right? So in effect, if you look at the server-based algorithm, what happens is that the server receives information from all the agents, such as gradients, and computes the next estimate and sends to all the agents. The server actually is trusted, non-faulty. And each agent in a peer-to-peer setting can actually simulate that server. And if they're simulating it identically, then all the agents will have the same state estimate at the end of every round. But for that to work, we need to be able to perform Byzantine broadcast. And Byzantine broadcast is possible if and only if these conditions are true. The number of agents has to be more than 3T, and the graph connectivity, the vertex connectivity has to be more than 2T. What I showed you was a complete graph, but in an incomplete graph, the connectivity can be smaller. But as long as it exceeds 2T and the number of agents is more than 3T, then any undirected graph, any undirected point-to-point network, we can perform Byzantine broadcast, and therefore we can simulate the server-based algorithms I'm going to discuss today. So there exists algorithms. In fact, one of the first fault-tolerant optimization algorithms that was proposed was actually performing these kinds of Byzantine broadcasts. But there also exist algorithms for the peer-to-peer setting, in particular for the complete graph. Such where we do not actually use Byzantine broadcast, meaning the fault agent can in fact send different values to different neighbors in that complete graph. Without having to do Byzantine broadcast, the algorithm still provides usable output. We won't discuss the details of those algorithms today, but there are pointers here if you would like to look them up later. So like I said, we're going to focus on the server-based architectures for the rest of today. So let's consider this algorithm that we have seen before. The server is trusted, and the server is maintaining the estimate xk. And in each iteration, the estimate is sent from the server to all the agents, and the agents are supposed to upload their gradient, and then the server computes the next estimate. Except that now, because some of the agents are faulty, the agent cannot simply, rather the server cannot simply aggregate all the agents, because if it did that, it's also aggregating the gradient from the bad agent, in this case, gradient from agent 3, and this summation can be essentially any arbitrary values because it is polluted by the faulty agent. So the server has to somehow get rid of the detrimental impact of the faulty agent. And for doing that, what the server is going to do now is to collect those gradients from all the agents and filter on them, meaning compute some function of those gradients and use that filtered gradient in this particular step, as opposed to the actual aggregate gradient. And other than that, the algorithm remains the same. And the question, of course, is how is this particular filter gradient computed? And for that, in fact, I will present a few different filters that people have introduced in various papers in related topics. And they all provide some useful properties, fault tolerance properties. Oh, I should point out that in this particular example, the gradients being uploaded here are the exact gradients of the cost functions, meaning agent one is uploading the gradient of cost function f1, exact gradient of cost function f1 at estimate xk, and similarly agent two, and so on. But instead, those gradients could have been stochastic gradients too, meaning this could have been a stochastic, instead of that could have been stochastic gradient sent by agent one. And then the filtering will have to happen now on this n stochastic gradients received by the server from the n agents. That's what this slide is saying. This is a deterministic case, or this is a stochastic case. And we saw stochastic algorithms previously. The filters have been applied for both the settings. And like I said, I'll introduce the filters soon. So the only difference between this slide and the previous slide is that the gradients are stochastic instead of the exact or deterministic gradients. And now this filter value is obtained by applying, sort of computing a function of the stochastic gradients. Okay, so like I said, I'm going to present a few different filters where the algorithm remains the same. The only thing that changes is the filter and whether the gradients are stochastic or deterministic. So I won't show you this slide again and again and again. The only thing we are going to discuss are the filters. What does the server do with these gradients it is receiving? The gradients can be deterministic or stochastic. So there are sort of various filters that have been proposed. I will discuss only a handful. And there are a variety of assumptions being made about the cost functions. So like I said earlier, either we assume that the gradients are exact or deterministic, or the gradients are stochastic. So that's one degree of freedom we have in this, are we working with these gradients or these? And then we might make assumptions about the cost functions. Either the cost functions are maybe identical or they are not identical. And identical cost functions are interesting, for example, in the machine learning setting, particularly with stochastic gradients. But if all the agents have the same cost functions, meaning f1x equal to f2x and so on, and the gradients being supplied are deterministic, then each agent or each fault-free agent must be supplying to the server identical gradient. And then the server's job is very simple. He's getting a bunch of gradients, right? N of them. As long as N is more than 2t, the server can just take majority vote of the gradients and use the majority vote as the filter gradient and take the step. Okay, so if the functions are identical and we're doing the full, the deterministic gradient, the problem is quite trivial. The problem becomes interesting for the identical cost functions if the gradients are stochastic. So even if the functions are all identical, the gradients supplied by the agents may not be identical because they are stochastic gradients. Actually, what I just realized I skipped over this box, so let's talk about this first. So in the setting where we're supplying deterministic gradients, if the functions are non-identical, then we have seen that the problem is not trivial, right? There may be redundancy, there may not be redundancy, or if there is redundancy, the redundancy may be of different kinds. We talked about two different kinds of redundancy, two-to redundancy, and the approximate case version of it. So some papers look at deterministic gradients, but with either redundant functions or functions that are not redundant. And then we get to the stochastic case. The stochastic case, the identical cost functions basically means that the agents are homogeneous. They all have the same behavior. To be more precise, the stochastic gradients that the agents are providing are drawn from the same distribution by all the agents. So the stochastic gradients are IID across all the agents. And the problem is not trivial anymore because the stochastic gradients are not identical, even if they're identically distributed. And so now the majority vote is not going to the right answer. You need some other filter perhaps. And then you have the non-IID. Actually, before I come to this, which is a non-IID case, let me give you a quick example of when this might actually happen. And we may have talked about this briefly earlier. So when would you have identical cost functions? One example of that is machine learning. So you may have different agents that are working with this trusted server to perform distributed optimization, but these agents may have access to identical data sets, right? Or they're drawing gradients from the same distribution. So if all the agents have access to the same data set or they're drawing from the same distribution, why do I need multiple agents? In fact, one agent will suffice to solve the problem because every agent has the same cost function. The reason we have multiple agents in this setting is for speed up. If there are lots of agents, then you can converge, you can compute, you can reach the convergence faster because more agents will compute more stochastic gradients. If you compute just one stochastic gradient, it will have a high variance. But if you have many agents computing stochastic gradients and then you aggregate them somehow, then the variance will be lower and we get faster convergence. So for the IID case, having more agents should give you speed up. But then we need to find a way of filtering on those stochastic gradients. And finally, the fourth box, which is that the functions are not identical and the gradients are stochastic. So this is the so-called non-IID model. So in the machine learning setting, the agents are supplying gradients from some distribution, and for the distributions are not the same across all the agents. And there has been work on basically all of these settings by now. So what I will do next is to introduce various filters. And I will try to summarize the context, from this slide, the context in which those filters were introduced. It does not mean that the filters will not work in other contexts. It's just that they were introduced for a particular context. So the very first paper in this space assumed that we know about, at least that I know about, was designed for fault-tolerant optimization for arguments that are scalars, basically a real number. And one can extend that filter to vector arguments by essentially applying the same filter to each element of the vector element-wise. And people have done that too by now. But the first paper really did not do this part, just looked at the scalar argument. So what is that filter? The filter is described here. So there are n agents of which up to t can be faulty as before. And if you recall this step size, lambda, that let me show you where lambda appears. Going back a few slides here, this lambda, right? So this step size can be constant, it can be decreasing and so on. So different papers will make somewhat different assumptions occasionally. The assumption made here, this is quite common, that summation of those lambda k over k is unbounded. But the sigma lambda square is bounded. So the filter is quite simple. This is sometimes called the trimmed mean. So the server gets n gradients, which are really just n numbers, n real numbers. The server will sort those numbers. It will throw away the t smallest values and t largest values. Then it is left with n minus t values. And the filter gradient is just the average of those n minus 2t values. Okay, so that's the very simple filter. The intuition is just you're just throwing away the outliers. This kind of filter has been used in other settings, in particular, the so-called problem of Byzantine Consensus, which can be thought of as a special case, a very special case of fault-tolerant optimization that we're discussing here. But this filter was used to achieve Byzantine Consensus or agreement in the case where some agents may be Byzantine. But now one can apply this to the case of Byzantine fault-tolerant optimization too. So here's an example. If there are 7 agents and up to 2 may be faulty, and let's say the server receives these values, the gradients from those 7 agents, then we are going to throw away the bottom 2 and the top 2, right, the red values. And then we'll take the average of what remains, which gives you 7 by 3. So this is the filtered value of the gradient that will be used to compute xk plus 1 from xk. And then we repeat this. In the next iteration, the server again gets 7 gradients, do the filtering, use the filter gradient to compute xk plus 2, and so on. In fact, this type of filter has been used in the setting where there is Byzantine broadcast and not Byzantine broadcast, both for the peer-to-peer case, but we won't get into the details of that here. So that filter has been by now applied for the case without redundancy, the independent functions. That was the original paper that I alluded to earlier. There was no redundancy assumed in the first case, but later on, the filter was applied to a setting where functions are redundancy as well. And that's what this is saying. So I'll point out in this manner for each of the filters I'm going to introduce. Again, like I said, even though the filter was introduced for this setting, it could be applied to other settings too, possibly. It doesn't exclude that. It's just that initially it was introduced for this setting. So I'll try to do this for other filters as well. So like I said earlier, even though that filter was introduced for real numbers, scalars, one can extend that filter to vectors by applying that same idea for each element of the vector. So if you get gradients that are, let's say, d-dimensional vectors, there are n of them, then we can take the first element of the n vectors and apply the filter to them and get the first element of the filtered gradient. Then take the second element of each of the n vectors, apply the filter to them, get the second element of the filtered gradient, and so on. And then you get the gradient that is a d-dimensional vector, that is the filtered version of the n vectors that you have received. And some people applied this filter as well by now for fault-tolerant optimization. Here's an example of that for the smaller case. Suppose n equal to 4, t equal to n agents, 4 agents, 1 can be faulty, and d equal to 3. There are 3 elements in the vector. And so if you just take the first element and throw away the smallest and the largest, what you're left with is 0 and 6. And the average of 0 and 6 is 3. That's how we get 3. And similarly, the last element is going to be, you throw away 3, which largest value, minus by the smallest value. We are left with 1, and so on. And similarly, you get this value by averaging 5 and minus 1. So that was the trim mean applied to scalars as well as extended that to vectors. Here is another filter that's called CRUM, and then a generalization of that called multi-CRUM. And so what does that filter do? So first define, I'm going to write the distance between two vectors uv this way. This is the norm of u minus v. That's the distance. We're going to call it the distance between vectors u and v. And then we're going to define a score of a gradient. Remember that the server receives many gradients. Let's call them g1, g2, gn. And they're going to compute a score for each of these gradients. So score for g1, for example, there are n minus 1 gradients left if you ignore g1. So score of gradient of gradient g1. What we're going to do now, we're going to compute the distance of g2 from g1, distance of g3 from g1, gn from g1, and so that distance of every gradient from g1, and then add up the distances of the closest n minus t minus 2 other gradients, right? There are n minus 1 such gradients. We won't add up all of them. We take only n minus t minus 2 of them. And that gives you the score of gradient g1. We compute score of gradient g2 similarly, and so on. And then the filter gradient is simply the gradient from among those n gradients that has the smallest score. Okay, so I think I have an example on the next slide. But before that, before the example, so with CRUM, we are using the filter gradient is just that one gradient whose score is the smallest. The generalization is to not just pick the one gradient with the smallest score, but pick m gradients whose scores are the smallest among all the n gradients. So for example, if m equal to 2, then we'll pick the gradient with the smallest score and the next smallest score and average those two gradients. That's my filter gradient. So CRUM is just a special case of multi-CRUM with m equal to 1. So let's take an example of CRUM. So in this example, we have n equal to 5, t equal to 1, then n minus t minus 2 will be equal to 2. And so suppose this is my gradient G1, G2, G4, G3, G5. Then the score for G1 is the sum of this distance and sum of that distance. These are the two closest vectors to G1. And if you stare at the picture for a minute, you'll find that my output is going to be equal to G1 for the crumb case, meaning G1 has the smallest score among G2, G3, G4, G5. And so the filter gradient will be G1 in this case. And the score is the length, this length plus that length for this particular vector. So this filter crumb was introduced for the machine learning setting for the stochastic optimization version of the problem, where the agents are identical in that they produce stochastic gradients with identical distributions, IID model. And then we're applying the filter on the stochastic gradients. So even though the gradients have the same expectations, the stochastic gradients are not actually identical. They're only identical in expectation. Now, so I introduced so far two different filters. And I have said that, the filter was introduced for this context, or maybe it can be applied somewhere else. The first filter, the trim mean, I said was introduced here, but perhaps we can apply it somewhere else also. And it turns out that that is sometimes actually true, that filter interest of one setting can be applied somewhere else. But there are some hidden assumptions that I'm not actually going to state because they're somewhat complicated usually. But for example, we said here that the assumption is that the functions are identical in the sense that the agents produce stochastic gradients with identical distribution. That's an assumption that's being made to argue that the algorithm provides some desirable fault tolerance properties. But often, most of these papers will make other assumptions too, such as these. And again, I'm not being very precise about them, but a common assumption is to bound the variance, if it is stochastic gradient case, is to bound the variance of the stochastic gradient. So it's not enough to have just highly distributed gradients, but you also want the gradients to have small variance or relatively small variance. And that's necessary intuitively speaking because we are filtering on stochastic gradients. If the stochastic gradients have very high variance, then the gradient I provide and the gradient that you provide may look like nothing like each other at all. And if that's the case, how can you possibly filter on them? Because one gradient has no relationship to the other gradient, right? If the variance is very large, the relationship is quite weak. And so the filtering is not going to be very effective. If the variance was basically zero, which is so the gradients are all identical, then the filtering will be trivial. We saw that you can do majority vote. But we don't have to go that far. If you have sufficiently small variance, then the filtering is still effective. So for example, the stochastic gradient generally point in the same direction, even if not identical direction. If they point within some angle theta of each other, then you can see that somehow you can make sense of that you can sort of look at the directions and think about filtering them on them somewhat reasonably within quotes. So that's one sort of assumptions people often make. The other assumption that is made is the upper bound on T, meaning, yes, n more than 2T, you need that anyhow in most cases, actually in all cases, because if there are too many faulty nodes, then you don't know who is faulty and who is fault-free. So you want to have at least majority nodes fault-free, but that may not be sufficient in general. Because again, these algorithms are greedy in the sense that in each iteration, I'm doing filtering on the gradients, and I'm not really trying to figure out which agents are faulty, which agents are fault-free. I'm not learning anything from the observations I'm making in this round that is useful the next time. And that forces us to sometime bound this. So this will be T over N approximately equal to half, right? But you may have to bound T over N by something much smaller than half, depending on the properties of the cost function that you have. So there are these additional assumptions being made that are different in different papers, depending on the context, which really makes it very difficult to compare different filters. So when you look at different papers and different filters, You need to really look at what assumptions they're making, look at very carefully the guarantees they provide on the convergence of the algorithm. In general, if the filter is simple, then it's going to make stronger assumptions. For example, majority vote filter is very simple, but I'm going to assume that all the functions are identical and I'm assuming deterministic gradients and identical functions, very strong assumptions, and that's why my filter can be that simple. So in general, a simpler filter will force you to make extra assumptions. Perhaps you need to have a strong bound on the variance of the stochastic gradient, for example, if the filters are very simple. Here is a simple filter, the so-called norm-based filter. Now here, actually, let me remind you that we are filtering on gradients. So gradients are vectors that have directions and length. The length of the vector is the norm we are talking about. So this filter ignores the direction altogether. It looks at just the norm. And I should have actually in this case, in this example, the gradients are going to be scalars, but in general, you're looking at the L2 norm of the, so I should have written this differently. In general, you're looking at the L2 norms, but here is the idea. There are n gradients. This algorithm, the filter looks at just the norm, the length of the vectors. And if you have vectors of various length, in this case, there are vector of 3, n equal to 3, and t equal to 1. So one vector has length 1, the other vector has length 3, and third vector has length 2. So let me sort them, 1, 2, and 3. It says that clip the largest t norms. Largest t in this case is this particular norm is the largest, t equal to 1, and equalize it to t plus 1 at largest norm. Okay, so t plus 1 at largest norm. So t plus 1 at largest norm in this example is this one. So largest norm is this. The second largest norm is that. So you want to make this norm equal to 2. How do you make it equal to 2? You take this gradient, which is the second gradient, and multiply it by 2/3. Keep the direction unchanged, just scale its length. And we just want to multiply it by 2/3. If length was 3, we multiply by 2/3, if the length becomes equal to 2, maintaining the direction. So that's the filter. It's very simple. And that's what you get. So we keep this gradient as it is, this gradient as it is. The n minus t smallest gradients remain unchanged. The largest t gradients will change and change only in their length, the magnitude of the vector, the length, but not the direction. And then you add this up, or if you want, you can average them. Doesn't really, multiplying by constants doesn't change the behavior of the algorithm. So you can add or average, doesn't really matter. Okay, so this is a so-called norm-based filter. It's called comparative filter because what is being done here is to cap, right? We are clipping the largest gradients. We are capping the largest gradient, but we are not making them, we are not bounding them by a constant. A variation of the algorithm will be to pick a fixed threshold. You could say any gradient that is length larger than 5 becomes length 5. Right? And the 5 is just a constant parameter that we chose for the algorithm. Here, how much we are clipping each vector, how much we are clipping the largest gradients depends on the length of the other vectors. So it's in comparison to the other vectors. And that's why it's called comparative gradient elimination. So this was introduced initially for the redundancy case, but then it's been applied to the other settings too. And in fact, now, if you recall, in my earlier discussion of exact redundancy and approximate redundancy, I said that here are the centralized algorithms. I will give you a distributed algorithm later. One can design a distributed algorithm for the exact redundancy and approximate redundancy case using this filter. For the correctness claims, one makes assumptions about the redundancy, such as 2D redundancy, plus additional assumptions, such as on the variance of the stochastic gradients or a bound on T over N. So extra assumptions are required beyond the minimum redundancy condition I stated because this filter is quite simple. The choice of the filter will affect the additional assumptions one has to make. So maybe one more filter before we try to wrap up. This is a geometric median of means. So given all these, let's say, m vectors, u1, u2, um, we are going to define the geometric median as a vector v that minimizes this quantity. So if you're u1, u2, u3, u4 here, you pick v such that the sum of these four distances is minimized if this is v. So that's the v we are going to choose. And so in this case, in the simplest case, the filter gradient is simply the geometric median of the n gradients, or more generally, instead of taking geometric mean of the n gradients directly, we take the n gradients and we're going to divide them into, let's say, n by 4, b equal to, actually I did the wrong, yeah, that's okay, yeah, b equal to 4. I did the wrong thing here. Yeah, so what I'm trying to say is that there are 4 batches, so b equal to 4 in this example, and each batch has size n by 4. So first step, we compute simply the mean of these n by 4 gradients, 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 and then take the geometric mean of the averages of these b batches. So we are applying the geometric mean to just b average gradients. But there are algorithms that use some version of this geometric median of means for the purpose of fault tolerance. And this was also introduced for the IID case for stochastic gradients, or some variations on this. And I had to say there are other filters that people are introduced to. I'm not trying to be exhaustive in this tutorial, but just know that that structure that I presented earlier, where the server collects the gradients, filters them, and uses the filter gradient to compute the next estimate, that's been explored quite a bit by now. And for the most part, the different solutions only vary in the choice of the filter they make, and then the assumptions they make about the cost functions. And sometimes they also vary, they differ in what they're able to prove about the algorithms themselves. What kind of convergence properties can they show, or what kind of approximate resilience they're able to prove. There are a couple of notable omissions that I want to point out because they differ significantly from the other papers. One is this notion of reactive redundancy, and then learning from history. So in the algorithms that we're discussing here, we are, in effect, actually, let me rephrase this. In every round of the algorithm, the server is filtering on the gradients, right? Because we know, or we assume, that there are up to T faulty agents. Now, that's a very conservative method, because in a typical system, if the system is well designed and at least there are good attempts at securing the system, chances are there should be no faulty agents at all. There should be no compromised agents at all in my system, no Byzantine adversaries at all. And so throwing away T gradients each round seems unnecessary in the best case scenario. But on the other hand, we want to tolerate against the worst case scenario, where we are saying the worst case is up to T Byzantine agents. So what this idea is to say, let's try to get the best of both, meaning let's try to get the performance or the overhead of the case when there are no faulty agents, and yet we want to be able to tolerate faults. So one simple idea, for example, is that maybe I should check every once in a while whether the gradients that the agents are supplying to me are actually indeed accurate. So I can deploy redundancy dynamically only every once in a while, in a randomized way, for example. So to put it another way, suppose I ask you for a gradient, and when you send the gradient to me, with some probability, I'm going to check whether you send the correct gradient or not. And I have a way to check for that, perhaps by using some other agents as my backup to replicate the work we just did. And if the server is doing this in a randomized way, in a manner that the fault agent cannot predict, then whenever the fault agent cheats, there is a non-trivial chance it will be caught. At least over time, it will be caught before it can tamper with the computation too many times. And so there are ideas of this sort that try to give you best of both the worlds that we did not discuss. And the other is also an interesting thought. All the algorithms that are discussed so far, they share the same structure, right? Where the server gets the gradients, filters, and then you go to the next iteration. The only memory that we carry from one iteration to the next is the estimate that the server has. The old gradients that we use in the last iteration, they have no bearing on what's going to happen in the next round. That history is not used, it's not retained. And there is work now that points out that actually using the history of the gradients, for example, has value. You can get better convergence results by doing that. And I did not cover that line of work here either. So you might want to follow these pointers and look up those papers. So this is, I think, almost my last slide for today. And it makes the point that I already made, that there are many filters that are incompatible as of this point, just because different papers make very different assumptions. And the assumptions are sometimes hidden. They may not be immediately obvious what the assumptions are. And even the form of the assumptions is not identical, meaning one paper may be bounding a particular quantity that is somehow capturing the variance of the gradients, but may not be the variance itself, maybe something as related to variance, whereas other paper may be bounding some other quantity, and again, making them incompatible. So you have to be careful when you're trying to compare different algorithms with each other. So with that, I'm going to wrap up. What we did in the last lecture and today, we discussed some simple basic results about fault-tolerant optimization and learning. And then we discussed a few simple filters that have been investigated by now for fault-tolerant optimization and machine learning both. With that, I'm going to stop here. So this concludes part 4 of the tutorial. Thank you.